Great, thank you very much. Well, this talk is also very much in the flavor of trying to apply quantum reasoning, let's say, to think about possibly new perspectives on free will and consciousness. At least I'm going to give you that, and I'll let you decide whether there's something interesting or not. But I need to start by telling you what invariant set theory is. It's an approach I've personally been pursuing for some years now as an alternative model of quantum physics, which is deterministic and locally causal. My own background is very much in the nonlinear dynamical systems theory, and invariant set theory is motivated very much by the fractal geometry of chaotic attractors. And its basic postulate is that the whole universe can be considered a deterministic dynamical system that evolves on some kind of fractal invariant set in cosmological state space. What that implies in turn is that the laws of physics at their most fundamental, if this idea is correct, somehow describes the geometry of this cosmological invariant set. As I'll talk about, what it leads to is a perspective on quantum uncertainty that's very much in the epistemic camp and not ontological. That is to say, uncertainty is our uncertainty about the world, not the world's uncertainty about itself. I would say the basic ideas were described in two papers just over 10 years apart, actually, published in the Proceedings of the Royal Society. I think they can be found on the archive as well. In addition, in the last year or so, I've published a number of papers on this in collaboration with Sabine Hossenfelder from the Frankfurt Institute and John T. Hanse from the University of Bristol. So I just want to give you a flavor of what invariant set theory is all about. And I just start with a classical system, which is the Lorentz equations, famous three-component Lorentz equations. And I've just shown a finite trajectory of those equations in the three-dimensional state space of those equations. And a trajectory is just a one-dimensional curve that maps out it's the integral curve of the differential equations which define the dynamical system. By contrast, in invariant set theory, we're talking about the geometry of a fractal attractor or a fractal invariant set. And the particular picture which has been developed to describe quantum physics is one where a trajectory in state space is no longer a single line, but on magnification, it's some kind of fractal helix. So it's almost, you could think of it like a piece of rope where you have pieces of rope wrapped around each other, and then the individual pieces of rope are comprised of pieces of rope, and so on and so forth. So if you took a cross section through that piece of rope, you look at something like B, and this cross section B is actually isomorphic or homeomorphic to the set of p-adic integers. So in fact, p-adic arithmetic is actually the appropriate mathematical form to describe things like time evolution on the invariant set because of the homomorphism between p-adic sets and fractal geometry. In part C, I show that this structure can unravel when the system or a system under interest interacts with the environment, and that can be thought of as corresponding to the decoherence of quantum systems. And then finally, this invariant set theory proposes that these trajectories ultimately group into discrete clusters, which you would identify as measurement eigenstates. Now, the key point about all of this, when one talks about fractals, is that there are gaps in between the trajectory elements associated with the fractals. They're fractal gaps. So if you look at B, you know, there are gaps at any scale. There are gaps in the fractal. And these gaps in state space can be thought of as counterfactual worlds, potential counterfactual worlds, which according to the theory would not be realistic because they would not lie on the invariant set. And the fundamental conjecture of the invariant set is that it describes all of the realistic states of the universe. And typically these fractals are measure 0 in the Euclidean embedding space. So this is a very important point when it comes to looking at Bell's theorem and non-locality in particular, because once you do not have the property of counterfactual definiteness, which is to say that all putative states could be potential states of your theory, then you can violate the statistical independence assumption in Bell's theorem. And you can do this without actually having to invoke fine-tuning or conspiracy or indeterminism or action at a distance. And this was always the original motivation for this idea, to come up with a theory of quantum physics that doesn't require action at a distance or indeterminism. So the key point is that the assumption is that fundamental laws of physics describe the geometry of the invariant set. And that in turn implies that any dynamical evolution law that you may have for our world is necessarily influenced by dynamical evolution in neighboring worlds on the invariant set. If you just think about that, just to go back, the p-adic neighborhood, the structure of the trajectory in any one point in this neighborhood will be affected by the trajectories in the neighboring in the neighborhood itself. So there are a number of consequences of this, things like to do with explaining quantum speed up, potentially explaining dark matter, potentially explaining the non-singular nature of space-time singularities. But this isn't a conference about that, so I'll pass over these points and come on to the point of the talk. And I was going to just briefly discuss a couple of things, why we feel so viscerally that we could have done otherwise, that we have this feeling of free will, which for a determinist kind of makes no sense. If a world is deterministic, then the idea that we could have done otherwise would be inconsistent with determinism. But nevertheless, we all feel, as I do, of course, that we have this sense that we could nevertheless have done otherwise. So why do we feel this? Why is it that we feel quantum physics is non-intuitive? Why do we? And then I want to, I'm not sure how the time is going, but I wanted to say possibly a couple of words on the problem of moral responsibility in a deterministic world, which is always one of the most difficult problems, I think, if one believes in determinism, in explaining why we have moral or should have moral responsibility. Hello?
You still have 7 minutes.
7 minutes, okay, that's great. And then finally, a possible mechanism for consciousness. So I am going to assume that human cognition is influenced by inherently quantum processes. I'll just say in passing, I personally believe that the fact that the brain operates on 20 watts of power, unlike say 20 megawatts, which a supercomputer runs on, actually requires it to run on inherently quantum processes. I don't think it would be possible for the brain to do what it does using purely classical processes if it only operates on 20 watts. But anyway, I will assume that, and I'm going to secondly assume that invariant set can describe quantum physics. So the first point then is I could have done otherwise may in fact imply this notion that we have a weak cognition of these neighboring counterfactual worlds on the invariant set in the p-adic neighborhoods. So it's not that we actually could have done otherwise, but we have a cognition of these neighboring worlds where we did actually do otherwise, because by definition they are worlds which are not identical in state space to our actual world. So this could be our sixth sense. On the other hand, our cognitive awareness of these neighboring worlds may be sufficiently weak that we're actually unable ourselves as humans to discern between counterfactual trajectories on the invariant set and counterfactual trajectories off the invariant set. And so we treat them all as intuitively plausible. Now, if that's the case, then we are going to get stuck with things like Bell's theorem. If we assume laws of physics which are counterfactually definite, then we will end up viewing quantum physics as non-intuitive. So that's my explanation of why we feel a lot of quantum physics is weird, because we don't have the cognitive ability to discern between counterfactual trajectories which lie on the invariant set and ones that lie in the fractal gaps. The idea of moral responsibility is the one that this is a quote from Imwagen, sort of standard quote about if determinism is true, then our acts are consequences of the laws of nature and events in the remote past. But it's not up to us what went on before we were born, and it's neither is it up to us what the laws of nature are. So that's the difficulty. If you believe in determinism, how can you believe in moral responsibility? Because everything that we did was determined at the time of the Big Bang. In invariant set theory, the initial conditions are actually not fundamental, and they're not independent of the evolutionary laws. The two are subservient to the invariant set geometry. And in fact, there's a kind of dualism, which is very similar to John Wheeler's dualism about general relativity, that space-time tells matter how to move and matter tells space-time how to curve. In this case, in some sense, it's invariant set geometry tells us how to behave, but our behavior also tells the invariant set geometry how to shape itself. So I believe that this could be a way of overcoming this very difficult, I think, problem of believing in the one hand in determinism, and the other hand believing in the fact that we have moral responsibility for what we do in our lives. And then my very last point is just to make some sort of speculative comments about consciousness. I have this cactus because right behind my laptop is a cactus looking very much like that. Photons that come off the light bulb or the sun when I'm looking at the laptop screen actually hit the cactus and enter my eye. The cactus is in my field of vision. But for example, in most of this talk, I haven't been aware of or conscious of the cactus because I've been focusing on this talk. So I'm aware of the cactus, but in a very undifferentiated way. It's complete. It's just one with the rest of my room and the rest of the world. But now, when I'm looking at the cactus, I become aware of the cactus and I become conscious of the cactus. So the question is, what does it mean to become conscious of the cactus? And I would claim that to be aware of it is to ascribe an existence to it that is independent of the other background objects in my field of view, to have finally this differentiated view of it as something different and separate from the other objects. And it could be maybe that this cognitive awareness of the cactus as an independent object, independent of other objects, is also a consequence of this proposal I'm making of a cognitive awareness of neighboring counterfactual trajectories on the invariant set. Because in these neighboring trajectories, indeed, the cactus would have a slightly different relationship to the other objects in my field of view. And so it is that cognitive awareness of the neighboring counterfactual trajectories on the invariant set which gives me this feeling of objects in the world having an independent existence to other objects, which I would view as being an essential part of being conscious of these objects. So that's the end of my talk. It's, I'm afraid, a very rushed presentation of a theory of quantum physics, which I have been, as I say, developing over a number of years and trying to apply it to some of these difficult problems of our own brains functioning. Thank you very much.